Hello everybody! So in today's video for Chapter 9, we're going to start looking at ways to identify more information that we would need for a graph. And in order to do this, we need to start by talking about solving quadratic equations. So sometimes we need to find the x-intercept of a quadratic equation. When we were doing our modeling problems, what we found is we often wanted to know when something landed or where it landed. And landed is another way to think about hitting the x-axis or finding the x-intercepts. So this would be where the graph crosses the x-axis. Now, when we have a graph, that's pretty straightforward, but if we don't have a graph and we're making our own, we're going to need to be able to solve. And one of the ways to think about the x-intercepts that helps us understand how to solve them is that these are the places on the graph where the y value of the ordered pair is equal to 0. So in order to start talking about how to make this happen, we need to understand something called the zero product property. What the zero product property says is that if the product, that means when we multiply, so if we multiply two or more numbers and the answer is 0, so if you know that you multiply and you get an answer of 0, then one of the numbers that you started with must have been 0. Now, we investigated this today in class, so what we're going to do now is look at some of the ways we can use the zero product property to solve equations. So solving this equation means figuring out what values I could use for x or for y so that when I multiply those two numbers together, the answer is 0. Well, since the answer is 0, in other words, the answer to a multiplication problem is 0, that tells me that one of these numbers must have originally been 0. So one way to make this product equal to 0 is to make x equal to 0. And another way to make this product equal to 0 would have been if y was equal to 0. And those are your solutions. Those are the answers. Now, there are three different ways to describe these solutions. These would be the x-intercepts is one way to describe those on a graph. Another word for that is the zeros, which means the same thing as the x-intercepts. It's just sometimes we call them zeros because it's the place where y equals 0. And another way that we sometimes name these things is what's called the roots, because that's where the graph would be rooted to the ground. Like a tree's roots go into the ground. These are the places where the graph would go into the ground, into the x-axis. So let's look at another example where we have to use the zero product property. So if we look at this equation, I can see that I'm equal to 0, which allows me to use the zero product property. What the zero product property says is that if I have a multiplication problem, which I do, and the answer is 0, then one of these original factors must have been 0. So either x equals 0 or x plus 2 equals 0. Now, x equals 0 is done. Like x just could be 0. But this part of my answer, where it says x plus 2 equals 0, we need to do a little bit more work because we need to solve this and figure out what x value would make that happen. So in order to solve this equation, we would just subtract 2 on both sides, and we would figure out that another way to make this happen would be if x is negative 2. Now again, these are the x-intercepts, meaning that this graph would cross the x-axis in two places, at the 0 and at the negative 2. We could also call them zeros because they're the places where the equation equals 0. And we could also call them the roots because it's where the graph is rooted to the x-axis. Let's do one more. So this next one, we've got x minus 5 times x plus 8 equals 0. Again, I equal 0. So as soon as I know that I equal 0, I can use the zero product property, which just says make each one of these factors equal to 0 by themselves. Now this time, both of these are going to need to be solved to figure out the exact x value that we're looking for. So I would just add 5 on both sides of the equal sign here, and I would get x equals 5. And I would just subtract 8 on both sides of the equal sign, and I would get x equals -8. So again, there are two places where this graph would cross the x-axis, at the +5 and the -8. There's also two places where the equation would equal 0 when x is 5 or when x is -8. Now let's take a look at how we might use this and do this if we didn't already have a product. So problems 1 and 2, the directions say solve by factoring. Now the reason that we're going to want to factor here is that when we factor, we turn an addition or subtraction problem into a multiplication problem. So by factoring, we create a product, which is what we needed in order to use this property. So let's take a look at number 1. In number 1, I can see I've got a polynomial. I've got x squared plus 4x minus 5. It's a trinomial, which is not a product. There's a bunch of things being added and subtracted from each other. So it's an adding and subtracting problem. But I can see that it's equal to 0. As soon as I see that this is equal to 0, that tells me I need to create a product. Because then I can use my zero product property. So in other words, I need to factor. Now when we factored, we drew boxes. The first term from our problem went in the first box, x squared, and the last term from our problem went in the last box, minus 5. Then we needed to fill in our middle boxes. So to do that, we drew a big X and we calculated our M and our A. Now our M in this problem would be -5 and our A would be 4. So a list of pairs that make 5 are 1 and 5, and then that's it. Now in order to turn this into a 4, I need to make the 1 negative. So I would use -1 and +5 in my boxes. So here I would write -1x and +5x. Then I just needed to factor. So the first column, they have an x in common. And then I can fill in the rest by thinking about what's missing. So if I want to make an x squared and I have an x here, I need an x here. If I want to make a 5x and I have an x here, I need to put a 5 here. If I want to make a -1x and I have an x here, I need a -1. And I can check myself by doing -1 times 5 and seeing if I really get -5, which is what I get. So that's good. So my factored version of this equation would be x minus 1 times x plus 5. And then I'm going to copy down the equals 0, because unlike when we first learned about factoring, this problem was originally an equation we needed to solve. Now what I've done is I've taken this problem where a bunch of things were added or subtracted, and I've turned it into a multiplication problem. So you can see here now I have x minus 1 times x plus 5. When I see that I have a product that equals 0, I make two separate equations because each one of these factors could have equaled 0, and that's what would have made my final answer equal 0. So finally, I would just solve each one of those separately. By adding 1, I would get x equals 1, and by subtracting 5, I would get x equals -5. And those would be my two answers. Now in the next problem, Again, I'm noticing that I have an addition or subtraction problem instead of a multiplication problem, and I know that I need a multiplication problem because I'm equal to 0. So I know that I need to create a product. Now in this problem there are only 2 terms. So I'm going to start by looking for the GCF, which in this problem would be x. And then when I factor that out, I would have parentheses 2x plus 3. And I'm going to drop down the equals 0. Now since there's no squared left, there's no power higher than 1, I've factored this as much as I can. So I'm going to go ahead and make each one of these factors equal to 0. So x equals 0 and 2x plus 3 equals 0. I'm going to solve this one, because this one's already done. X equals 0 is already solved. So I'm going to subtract 3 on both sides, and I'm going to have 2x equals negative 3, and then I'm going to divide by 2. So I'm going to have x equals negative 3 over 2 as my answer. And those are my 2 answers. Now you might be wondering how we incorporate this into what we already know. So what we already know is that we know how to graph these equations, but now we're going to be able to make more detailed graphs because we're going to be able to identify the x-intercepts. First, we're going to determine whether this opens up or down. Because the leading coefficient here is a 1, this parabola will open up since that is positive. To get the vertex, I need 2 different components. I need an x and I need an h. So my x is going to be negative b over 2a, which is negative 7 over 2 times 1, which is negative 3.5. To figure out my y, I'm just going to take that value, the negative 3.5, and I'm going to plug it back into my original equation. So y will equal negative 3.5 squared plus 7 times negative 3.5 plus 6, which when I type that into my calculator, gives me negative 6.25. The axis of symmetry will go through the same x value that I got here. And so I'm going to have x equals negative 3.5. And the y-intercept is usually the easiest part because it's just the c. It's whatever the last number is, 6. To get the zeros, otherwise known as the x-intercepts, I need to make my y equal to 0. So since f of x means the same thing as y, all I'm going to do is put a 0 there and make that equal to my original equation. Now we know that we need to turn this adding and subtracting problem into a product. So I'm going to do that by factoring. So my x squared, which is my first term, goes here. My 6, which is my last term, goes here. I know that the factors of 6, I know that my m is 6 and my a is 7. And I know that the factors of 6 that will make 7 are 1 and 6. So I'm going to put a 1x here and a 6x here. Then I'm just going to factor. So this column has an x in common, which means this has to be an x, and this has to be a 6, and this has to be a 1. So my new factored equation is, I'm going to bring down the 0. 0 equals parentheses x plus 1, parentheses x plus 6. And then I'm just going to solve by making each one of these factors equal to 0 separately. When I subtract 1, I get x equals negative 1, and when I subtract 6, I get x equals negative 6. So now, let's graph. First, we're going to graph the vertex. So the vertex is going to be at the point negative 3.5, negative 6.25. So right about there. The axis of symmetry is going to go right through the vertex. The y-intercept is going to go on the y-axis. And remember, buy one, get one free. So if this is 3.5 spaces to the right, I need to now go 3.5 spaces to the left and put a point there as well. Finally, the new thing to make a better graph is that my zeros, or my x-intercepts, meaning they're on the x-axis, would be at -1 and -6. Then I'm just going to draw my parabola. And there we go. Last but not least, how would we use this in a modeling question? So it says here the height of the tennis ball after it is hit is modeled by this function, where h is the height of the ball measured in feet and t is the time measured in seconds. When does the tennis ball hit the ground? As soon as I see hit the ground, I think to myself, that is the x-intercepts. That would have been the places on the graph where the tennis ball hits the x-axis, which we learned in our modeling part of the chapter. So, in other words, I need to take this equation and make it equal to 0. So instead of h of t, I'm going to write 0 equals this equation, -2t squared plus 7t plus 4. Now again, I'm going to need to factor, so I know that my first step here for factoring would be to take out a -1, because that would be the common factor. Then I'm going to draw my boxes. So my 2t squared would go in the first box, and my -4 would go in the last box. I'm going to draw my big crisscross. My m would be -8 and my a would be -7. So the factors of 8 that make -7 are 1 and 8, and I would just make the 8 negative. I would have 1t here and -8t here, and then I can just factor. So this column has a 2t in common, which means this must be t, this must be -4, and this must be a 1. So my new equation will be 0 equals, and instead of this part, I'm going to write -1, parentheses 2t plus 1, parentheses t minus 4. Now you'll notice we have a -1 here, but because -1 is just a number, it's never going to equal 0. So even though that would be one of my factors, it doesn't really matter that it's there because -1 will never equal 0. Then I would have 2t plus 1 equals 0, and then I would have t minus 4 equals 0. So 2t plus 1, I would subtract the 1 on both sides. I would have 2t equals -1, and then I would divide by 2 on both sides to get t equals -1/2. For t minus 4, I would just add 4 on both sides, and I would get t equals 4. So it kind of seems like there are 2 times when I would equal 0. I would hit the ground. However, you'll notice that this time is negative. Now, it's impossible for our time to be negative. You can't go backwards in time. So this is what we would call an extraneous solution, which means this is a solution, but it's extra. We don't need it for this problem because it doesn't make sense in a real-world context. So t equals 4 would be my only answer, and I would label that seconds because in this problem the time was measured in seconds. Alright, I know this was a longer video. I'm hoping that what you saw today made sense, and I will definitely see you in class for some practice. Thanks for watching.